Okay, so let's go on and have a look at the nature of the first fixed point. So we can set up the linear differential equations by subtracting from the vector of derivatives the result of multiplying the matrix, the Jacobian matrix evaluated at the first fixed point, times the vector of variables, and we can do that using this. And we try to solve these equations or find a solution of these equations in the form of a constant vector r, whose coordinates we can, or whose components we can establish using that, multiplied by an exponential function involving a parameter lambda. So this is what the solution looks like. And if we want to put that into the differential equation, then we need to differentiate that with respect to t. So that's the derivative of our solution. And we now insert those into the linearized differential equations. So this assigns the value of the solution to the variables, and this assigns the values of the derivative to the derivatives. So the result of that can be seen using this, and we can see that this has three components. Each of these must be 0, which are each component is one of the elements of these the constant vectors multiplied by some things. So this is actually a set of, if we set it equal to 0, a set of homogeneous linear equations for the three components of the constant vector. And we can look at that in a sort of form of mathematics. It's e to the lambda t times lambda times the components of the vector minus the matrix J times R, and that can be, we can write lambda R as lambda times the unit matrix times R, and then that factors nicely into that. So this will only have a solution, or a non-trivial solution, if this matrix is singular. So let's work out this matrix. Here it is here. And the condition that this matrix be singular is that the determinant of the coefficients be 0, which is symbolically this, and we can work this out here for our matrix C using this. And what we see is that this is e to the 3 lambda t times lambda plus beta times this quadratic polynomial in lambda. So it's this can never be 0, so the result is that this cubic polynomial must be 0. So we can solve that for lambda using this, and this is what we find. And there are a couple of cases actually. The case when, we need to look at this for a bit first. And if all three, these are called eigenvalues, these values of lambda, and if all three eigenvalues are negative or have negative real parts, the fixed point will be stable. And why will that be? Well, simply because each one of these guys here will tend to 0 as t tends to infinity, if all the lambdas are negative or have negative real parts. So let's, to see that, let's clearly this eigenvalue is negative, provided beta is positive, so let's plot the other two. And I've plotted them for sigma and beta equal to their canonical variables, and for both eigenvalues, and then plotted those as functions of rho. So we can look at that, and we can see that the blue eigenvalue, which is the second one, starts off at 0 and is positive, and the red one is negative. So this fixed point has, generally speaking, one positive and two negative eigenvalues. So such a fixed point is said to be unstable. Well, the case rho equals 1, I think we will not worry about, because we've coped with it here. Anyway, so now we go to the second fixed point, and we evaluate the Jacobian matrix at the second fixed point, and there it is there, and we can see that this matrix is real provided rho is greater than 1, and for that we can calculate this characteristic polynomial, which was the condition we had that the equations had a non-trivial solution, using this, and we again see that this is a cubic equation for lambda, a little bit more complicated than the one before. So what we could try to do is to solve it. So we set the characteristic polynomial equal to 0 and solve it. And what we get is a mess. Okay? So this formula, which involves complex numbers and goodness knows what, is very complicated and therefore of very little use. Anyway, before we pursue another strategy, let's look at the third fixed point. We calculate the Jacobian matrix at it using this, and then the characteristic polynomial, and we can compare that with the characteristic polynomial associated with the third fixed point, and if we look at those carefully, we'll see that they're the same. So in other words, the third fixed point will have exactly the same properties as the second one. So now we want to look at their stability. So what we really want to do is to find out something about these fixed points without actually finding them. Well, one way of doing that is to differentiate the characteristic polynomial, because if this derivative is 0, this means that the characteristic polynomial has turning points. Well, if it has real zeros. On the other hand, if the quadratic has no real zeros, then it will have no turning points, and therefore be monotonic, and therefore only have one real zero. So the condition for that is that the discriminant of the derivative of the quadratic equation for the derivative, which we can calculate using this, then there'll be no real solutions if this quantity is negative. Well, we can see that this quantity is linear in rho, so it will become negative for a sufficiently large value of rho, and we can find that value using this. And let's see what its numerical value is for the usual values of sigma and beta. It's about 13. So we can plot this for values of sigma and beta using this, and you can see that this value gets bigger here. Okay, so now we want to find the sign of the real part of the complex eigenvalues. So what I'm going to do now is to plot the characteristic polynomial for various values of rho for the standard values of sigma and beta. And here we see that the characteristic polynomial has a turning point here and here, but it never gets down to the axis, so there's only one real zero of the characteristic polynomial. We can put 5 into here and plot that, and you see that the same is true. So it looks like there is never more than one real zero. Let's put 15 in and plot the characteristic polynomial, and now sorry about this, it happens sometimes, and now we see that as predicted the characteristic polynomial is monotonic. And now we go to the canonical value where all the simulations have been done, 28, and the same is true.